So coming up next time is your Unit 1 exam, so we want to review for it. So that's what we're going to do here. I am here holding the Unit 1 exam. I'm waving it in front of the class. And what I'm going to do is base my review on what I see in front of me here. Okay, so you should get the real deal. Of course, let's take a look at what the whole thing is about. Unit 1 was called Constant Velocity Motion. And it was all about developing models that describe that describe an object that's moving with constant velocity. And well, first we had to define some terms though, right? Before we could define what velocity was, the first thing we had to do is define where something is in space. So to define where something is in space, we have to have an origin. We have to have a place where we all agree we know where it is. And then we have to compare where something is to that origin, and that's what we call position. So we have a number line here, the x position axis, and everything we did in this unit is along a straight line. We're going to get to two-dimensional and even three-dimensional motion later in the year, but let's keep it simple and just have something running back and forth along a straight line. And if we use these little toy cars, you know, with little lights and everything, and we said that we measure their position compared to our origin, and we called this x initial, and it is measured from the origin to where the object is located. If the object moves, in a later period of time, it was over here, we called that, let's put it over here, x final. So here we have the final position, here we have the initial position, and again, both of these position vectors are measured from the origin. And so we had a change in position. And that is the difference here between x final and x initial, or it's the vector that describes, okay, I started here, and I moved over here. So this was my delta x, my displacement vector. And we said delta x, by definition, was the final position minus the initial position. And of course, delta x could be negative. If the object was moving in this direction over time, your final position minus your initial position would give you a negative value, and that negative value is cool, right? You can have a delta x that's negative. It just means it's moving to the left instead of to the right. Now, it took time to go from here to here, so we take that and we take that displacement and divide it by the time, and we call that velocity. More specifically, average velocity. But we're going to talk about instantaneous velocity and all that later on in the year. And we abbreviated that with a V like this. Now, of course, one of the first things we did was we plotted position as a function of time. And this gave us our graphical model. And we said, like, if an object was right here, that was its position on the x-axis when time was 0, right? Here's the time axis when time is 0 at the origin here, and these are both 0. You say, oh, this position when time is 0, and then we release the object, and it moved over time, increasing its position. And remember, the motion is along the x-axis. This is, if you were to actually physically watch the object move, it would move up the x-axis like this. But of course, what we do is we take that motion and we spread it out over time. And when we do that, it draws a straight line. So we could plot points, and that's one of the things you're going to have to do. I'm going to give you position as a function of time data. You're going to have to draw the graph. Okay, and you'll see that it's a straight line. And we said, oh, this is a straight line. So we can model it using a mathematical equation. And we said that, well, y equals mx plus b is my general equation for straight lines. But in this case, I don't want to use y, because I'm now calling this the x-axis, or the position axis, position on the x-axis. This was the slope, right? M is the slope, and that's the change in height over the, the rise over the run. Well, what was the rise? This was some delta x, this was some delta t. And then, so there's your slope. And then instead of the horizontal axis, instead of being called the x-axis, we're going to call it the t-axis. Plus, and instead of b, well, that's the position when x equals 0. And so we get our general formula or equation that describes constant velocity motion. This is velocity times time plus our starting position. And there it is. Our position as a function of time is the velocity times time plus my starting position. And that is my mathematical model. And there was one other model that we introduced later on. If I took my x-axis, as I've drawn it here, redraw it over here. So again, this is x, not t. And I would draw dots. And I'd say, okay, at t equals 0, my object started here. And then every second, I would draw a dot that showed where the object was. And with constant velocity motion, these dots are all the same distance apart. And these little arrows, so this is at time t0, then 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. And then maybe we don't know what's happening after that. That's enough. And then it was just a matter of using all of these ideas to solve problems. And that's basically what the exam is all about. So in problem number 1 on the exam, this is what you're going to have to do. I'm going to give you, you're going to be given data, time in seconds, position in meters. So I'm going to give you a bunch of data. And then I ask you to do a lot of stuff with that data. First thing I'm going to do is say, graph it. Now, how do you lose points just by graphing data? Well, if you don't label your axis, if you don't plot the points correctly, if you don't increment correctly. Now, I would highly recommend that you have a sheet of graph paper to use on the exam. So now most of you have graphing paper notebooks, so you can just take a page out of your notebook. If you are using a college rule notebook, get some graph paper and bring it, because it's just going to make it a lot easier, because you're going to graph a lot. So you're going to draw the graph, and then you're going to write the equation for it, and you're also going to describe. I'll give you 2 points of time and ask you for what was the displacement, and then also, one thing. What's the difference between distance and displacement? Okay. Well, distance is the total amount. It's the total length of the path that something walked or moved. Okay? So if something starts here and goes this far and then turns around and comes back, the displacement is just from here to here. That's the displacement. But the distance, I go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this would be like 15 meters would be the distance So it's just the length of the path that was traveled, whereas the displacement is the difference between the final position and the starting position. And so in this case, this might be, if this was like 5, 10, 15 meters of distance, this would only be 5 meters of displacement. So do know that the difference between distance and displacement. Sometimes they're the same thing, aren't they, right? So what if you went from here to here? Okay, the distance would be 10 meters, but the displacement would also be 10 meters. So it'd be the same thing. What about from here to here? You started here and you went here. You say, oh, the distance is 5 meters. But what's the displacement if you went from here to here? It'd be negative 5 meters. So you got to, you know, distances can never be negative, but displacements can be. Okay. Oh, one other thing that you can do, if you're given a graph like this, and you will have to do this in number 1, if you're given a a position versus time graph that looks something like this, you can draw the velocity versus time graph. Right underneath it, right, a kinematic stack. And you say, oh, okay, this slope is positive and constant, positive and constant. Now, if you know what this slope is, if you know what it is, then you can make this a quantitative graph rather than a qualitative graph. Right? A qualitative graph doesn't have any numbers associated. You're just describing what the graph kind of looks like. So, looking at number 1, I'm going to give you position as a function of time. I'm going to ask you to graph position as a function of time. I'm going to ask you to graph velocity as a function of time. I'm going to ask you to write the mathematical model for that position as a function of time. I'm going to ask you a question about displacement and distance. So make sure you know that. I'm going to ask you to draw a motion diagram for this. Okay, for every second. And it's going to be a quantitative motion diagram. And then I'm going to ask you the average, like average velocity and average speed. Okay, so A, B, C, D, E, F. There's that many sections for it. Now, remember the difference between between velocity and speed, average velocity and average speed. For average, I'm running out of room here. Remember, for average speed, you calculate the distance traveled and divide it by the time. So figure out how much distance, what the path length was during that time interval, and divide it by the time interval. Whereas average velocity, as we've already said, equals displacement over time. Okay, and these can be very different. These can be in some situations they're the same thing. Average speed can never be negative. Average velocity can be negative. What does the negative mean? If an average velocity is negative, that just means your average velocity was to the left instead of to the right. So it means direction. Average speed doesn't include direction. Average velocity does. Okay, so that takes care of number 1. Let's talk about number 2. Now, number 2, I give you a motion diagram, and then you're going to have to draw the position versus time graph. Okay, so given a motion diagram, and then what you're going to have to find, well, in part A, you're going to need to draw the position versus time graph. And the velocity versus time graph. And this is going to be quantitative. I'm going to give you enough numbers so that you'll be able to draw it exactly. And actually, students find that easier than qualitative for some reason. But you're going to have to draw it as a kinematic stack. So what does that mean I'm going to require you to do when you draw these graphs? The position and velocity graphs are going to have to be stacked on top of each other. Make sure you label everything correctly. Now this, when you take this motion diagram, it's going to look kind of goofy. It might look something like, you know, like you increase and you do this and then you go maybe go up again or something when you plot it. So you're going to have to say, okay, during this time my velocity was positive and this is 0 and this is a little more positive, something like that. So you're going to have different time intervals, okay, where, you know, where these are going to be different velocities. But I think we've done that so you can handle that. Okay. And then this is A and this is B, but I want A and B as the kinematic stack. And then C and D, again, I'll give you a time interval, and you have to figure out average velocity and average speed. Okay, so just look at your starting time and then just measure the length of the path and divide it by the time. That'll be your average speed. And then for average velocity, you look at the final position, subtract the initial position from it, and you'll get the average velocity. Okay? Yeah, sorry it's so hot in here. The air conditioner broke. They are supposedly working on it. Okay, and that's it for number 2. Okay, number 3. Number 3 is kind of like the buggy car problem. This is when you use more than one mathematical model for the motion of where you have a mathematical model for 2 different objects and you graph them together. So the first thing I'm going to do is I'm going to give you a car A equation and a car B equation. You know, its velocity, its starting position, and okay. One of them might be negative, the other one might be positive, so that they're going to collide coming towards each other, or they might be both positive or both negative, but one will pass the other. And I'm going to ask you when and where the 2 cars will either collide or pass each other. So if you understood the buggy car lab, you'll be in great shape if you can solve those equations simultaneously. So I'm going to give, this is what's given. And then what you're going to have to find is, well, for A, I'm going to ask you to draw a graph. Graph the position of car A and the position of car B as functions of time. Okay, and then from that graph, you know, decide when and where they collide or pass each other. And then for part B, you're going to have to use the math models to decide, you know, when and where they collide. Did I spell collide right? 2 L's? All right. So that's number 3. And then number 4, just practicing this more and more. And number 4, I give you, here's what's given. I give you a velocity versus time graph. So you're given, on a graph you're shown what the velocity is of an object, and the velocity does change a little bit. And then here's what you're going to find is you need to find, from that, you need to use this graph to draw a position versus time graph. Okay. So what I would do is redraw this, and then above it or below it, like a kinematic stack, draw the position versus time graph. I tell you where to start. Because remember, with the velocity versus time graph, if that's all I give you, it doesn't really tell you where to start your position versus time graph, but I will tell you where to start it. Okay? And then you draw it as best you can. And then you'll need to draw from that. And then, oh, you're also given, I'll give you this. Where do you start when the position is 0? And then from this, you're going to draw the motion diagram. So study that. And that's pretty. And that's every second you draw a dot. So every second, figure out where it is every second. I don't know, I think on the test it only goes up to 6 seconds, so it's really not that big a deal. And then make sure that one thing that you need to know is what does the area underneath the velocity versus time graph look like? I mean, if I give you, I won't give you the one on the test, but what if I give you, like, this is 1, 2, 3, this is velocity in meters per second, and this is time in seconds, and this is 1, 2, 3, 1, 2, okay, and then 1, 2, 3. So what does this area underneath this graph represent? Well, I say, oh, I'm going 3 meters per second for 3 seconds. How far, what does that mean? I mean, the area is 3 times 3, right? So 1, 2, 3, 4, 5, 6. So what does this hashed in area represent? 6 what? Well, let's see. It's height times width, right? It's a rectangle. Height is 3 meters per second. Width is 3 seconds. 3 times 3 is 9. 9 meters. So this represents my displacement. The area underneath the velocity versus time graph represents displacement. And then this right here, what about this guy? For these 3 seconds, what was the displacement? Say, well, okay, it's got 2 times 3, would that be 6 meters? So the total displacement, it would be 15 meters? No. It's negative 6 meters. Now, what does the negative mean? It means, it means you walk to the left instead of to the right. So here we walked 9 meters to the right, and then we walked 6 meters to the left. So what total displacement did I have for the whole time interval? Well, that'd only be 3 meters of displacement. Does that make sense? So anyway, that's it. I'm pretty much giving you a very detailed accounting of what is on the exam. So study all your homework. Make sure your notebook is completely finished and you star and question mark everything. Review some of the videos if you want, but be ready because the test is on Wednesday. But it's very, very doable test. That is all.